Okay, in this video, we want to take two examples of applying implicit differentiation when we're dealing with transcendental functions. In the first case, we have e to the x is equal to the sine of x plus 3y, and we want to solve this for dy dx. And in the second example, we have the tangent of y equals e to the x plus the natural log of x. And again, we want to solve this equation for dy dx. So, for these examples here, we do what we've been doing all along, going through the equation and taking derivatives of both sides of the equation with respect to x. And matter of fact, let's make it a little bit more challenging. Let's make it e to the 2x power. So if we take the derivative of this, that would be e to the 2x times 2. Now if we wanted to be real formal, we would say it's e to the 2x times the derivative of this, which would be 2 times dx. dx, we're taking derivatives with respect to x. Of course, this is just 1, so we typically don't bother to write that down. And that will equal the derivative of this side of the equation. We're taking the derivatives now with respect to x. Okay, the derivative of the sine, of course, is plus the cosine of x plus 3y. And then we have to take the derivative of what is inside of here with respect to x. So this will be times, and I'm going to write it like this so we don't confuse this expression with what we're taking the cosine of. Okay, the derivative of x with respect to x, it's dx plus 3 times dy dx. And of course, dx dx, that's just 1, so let's write it like that. Okay, so we have then that the cosine of x plus 3y times this expression here equals this. We want to solve the equation for dy dx. So the first thing we can do is divide both sides of the equation by this and bring it over to here. But dividing by the cosine of x plus 3y, that's the same thing as multiplying by the secant of x plus 3y. So here, on this side of the equation, we'll have 2 times e to the 2x times the secant of x plus 3y will equal 1 plus 3 times dy dx. Now when I'm solving for something, in this case dy dx, I have to write it on the left-hand side. So we're going to have here dy dx it will equal this minus 1. So I have 2 times e to the 2x times the secant of x plus 3y minus 1. That would be 3 times dy dx. Divide both sides of the equation by 3. And there we have dy dx. And that's it. That problem is finished. So, again, if you were to look at this equation here and say you wanted to find dy dx, there's no way that you could look at it and just divine somehow that it would be equal to this expression. Nobody can do that. What we had to do is use the techniques. And we differentiated both sides of the equation with respect to x. And look at here now, we're taking the sign of two different variables here. It's not just the sign of x, it's the sign of x plus 3y. So we have to remember that when we take our derivatives here. And we're taking the derivatives with respect to what variable? X. So here, this part is no problem. The derivative of the sine is plus the cosine. Now we're taking the derivative of what's inside of the cosine, so to speak. And we're doing it with respect to x. So dx dx, that's 1, plus 3, that would be dy dx. And of course, this is what we want to, this is what we're solving for. Once we do that, the rest of the problem pretty much just falls into place. We're dividing both sides of the equation by this to get this, and then subtract 1 and divide by 3, and there's our answer. Not complicated. We're just using the techniques that you've been using all along, and just kind of following through step by step. So let's see how well it works for this problem here. Alright, we have the tangent of y, and that is going to equal e to the x plus the natural log of x, and we want to find dy dx. So again, taking the derivative of both sides of the equation with respect to the variable x. So this would be secant squared of y times the derivative of what's inside here, which would be dy dx, and that will equal the derivative of this side of the equation with respect to x. And the derivative of that is e to the x times the derivative of this, but that's just dx dx, that's just 1. Typically we don't write it down. Plus the derivative of this, that's 1 over x. And then it's the derivative of what's inside of here, but again, that's just dx dx, which is 1. So usually we don't even bother writing these down. So here we have then that the secant squared of y dy dx equals e to the x plus 1 over x. We can divide both sides of the equation by this, and we'll have dy dx equals e to the x plus 1 over x, and divided by the secant squared of y, that's the same thing as multiplying by the cosine squared of y. So this would be times the cosine squared of y. And there's our dy dx. So from this equation here, we wanted to determine dy dx, and here it is. And again, there's no way you could just look at this and somehow divine that this would be your expression. There's nobody that can do that. But if we use our techniques here and just follow it through, and there it comes right out. Okay, so we just want to try to provide a couple of quick examples of using the method of implicit differentiation when we have transcendental functions that we have to work with. That's it for this video, though. Come back and join us for some more videos, and we'll try and solve some more problems.